Prosthesis control is difficult because our available control signals are noisy and our feedback is limited. It's a bit like trying to untie your shoelace with a cold, numb hand, only harder. About 2006, I was working in a variety of areas of prosthesis control. How to make mechanisms and control more biomimetic, how to create more intuitive sensory portals. And it seemed that every direction I turned, I was getting surprising results. Subjects didn't like biomimetic control. Feedback didn't seem to help. Clinically, I had more questions than answers, and what little common sense we did have from clinical experience didn't make sense in the conventional paradigms used by my scientific colleagues. I realized that not only were the answers wrong, the very questions we were asking didn't fit reality or provide satisfying answers. In the words of Thomas Kuhn, we needed a scientific revolution, a paradigm shift, but I had no clue how to find one. Over the next several years, I turned the focus of my lab towards body-powered and mechatronic mechanism design, developing devices that are currently being tested in field trials. If I couldn't improve control, at least I could design better devices. But our perspective on control kept nagging at the back of my head. And finally, in 2012, the eureka moment happened, when Conrad Cording introduced me to the field of computational motor control. Computational motor control was asking the right questions, and had developed an impressive track record over the last decade answering them in able-bodied subjects. Basically, computational motor control frames everything from the perspective of uncertainty. How uncertain are your movements? How uncertain is your feedback? And at first glance, it makes some pretty wild predictions, like you should be more willing to adapt if your control is worse, rather than just giving up. We've recently shown that's true, even of amputees using noisy myoelectric signals, which we're really excited about. So now that we're asking the right questions and getting the right answers, we're building a model of how amputees control prostheses. And once we have that model, we can crank through every possible control technique we can conceive and every possible feedback solution available. And we can pinpoint the ones that are most likely to actually improve control. Testing these optimized strategies in field trials should rapidly accelerate the pace at which we introduce control improvements in a clinical setting. So we're really excited by our preliminary success and the hope computational motor control brings to a radical shift in how we view the field. To deliver on that promise, we're looking for talented members to join our team of clinicians and scientists to develop and test our models on amputees.